seminar. It's a great pleasure to introduce Dr. Daehyun Kim from the Division of Ocean and Climate Physics at Lamont-Doherty Earth Observatory of Columbia University. So Dr. Kim did his bachelor's degree in atmospheric sciences at Seoul National University in South Korea, in Seoul, South Korea. And then he proceeded to do his PhD in the same school, and his advisor was Professor In-Sik Khan. And his PhD dissertation was about cumulus parameterization in climate models and its impact on the simulation of the Madden-Julian Oscillation. Subsequent to his PhD in 2010, he became a postdoctoral research associate at Lamont, and recently he has been promoted to the position of an assistant research professor. So Daehyun Kim has had a very, is having a very productive research career. He did his PhD in 2010, but he is the author or co-author of 24 papers in peer-reviewed journals. He is a member of the Madden-Julian Oscillation Task Force in the World Weather Research Program of the WMO, and the American Geophysical Union has selected him for the James Holton Award this year, which will be presented to him at the AGU annual meeting in San Francisco in December. So and he has done very original work on the very difficult topic of Madden-Julian oscillation. So let us welcome Dr. Daehyun Kim.
Thank you for a nice introduction. So today I'm going to talk about simulation of the MJO using general circulation models. So I'll be talking about mostly the progress we have been achieved and a little bit about my perspective to future of MJO simulation. So let me briefly talk about my collaborators, my postdoc advisor Adam Sobel, my PhD advisor Professor Kang, and the Professor Eric Melanie, Professor Dargan Fierson, and Dr. Anthony Delgian at GISS, and Ivo helped me to get simul data. And also I have to acknowledge MJO Task Force, from where I started MJO work during my PhD period. So let me first introduce you what is MJO. Yeah, so the MJO is the organized convection in the tropics that propagates eastward with specific temporal and spatial scale. Temporal scale is planetary, and spatial scale is, temporal scale is 30 to 60 day period, and spatial scale is planetary. I don't know why this word disappears here, but MJO is dominant intraseasonal variability in the tropics. So it explains about half of intraseasonal variability in the tropics. This animation shows you what MJO looks like. So this is anomalous precipitation associated with the MJO during boreal winter time. If you look at this animation, the bluish color means anomalously high rainfall, and reddish colors is kind of relatively dry condition. And you can see that MJO-related convection develops over the Indian Ocean, and it propagates slowly eastward and reaches the Western Pacific and dies when it meets the cold SST over the Eastern Pacific. MJO modulate, like you just saw, tropical convection, so it affects the global circulation. So in this animation, the solid line is positive rainfall anomaly, and dashed line is negative rainfall anomaly, and you can see associated circulation all over the world. So, like by modulating global circulation, it interacts with many other climate phenomena, such as Indian and Australian monsoon in this region, and tropical cyclones in almost all basins, like the Western Pacific, Indian Ocean, and Atlantic. Also, it interacts with some El Nino events. Sometimes El Nino triggers some El Nino events. Sometimes it MJO terminates some El Nino events. Not even in the tropics, MJO also affects some heavy precipitation events in the extratropics through this teleconnection. Also, it interacts with the Arctic and Antarctic oscillation. So, understanding MJO and its relationship, its interaction with this many other climate phenomena, it's a great challenge for us. So this is the why the MJO is important. The second point, MJO bridges the predictability gap. When I say predictability gap, I mean the predictability gap between weather and seasonal prediction. So the predictability of weather forecast is in the initial condition. So we assimilate observation to the model to make the accurate initial condition, and it leads us better prediction. For seasonal prediction, we rely on ENSO. So we can predict the lower boundary condition in the tropics with more longer time. Then that provides us the predictability of extratropical weather. So we have some clear gap between weather forecast and seasonal prediction, and people have been working on that and found Madden-Julian oscillation provides predictability in this time scale. So let me summarize this very brief introduction to the MJO. It has a planetary scale, 30 to 6 day period, and it propagates eastward. MJO interacts with a wide variety of weather and climate phenomena globally by modulating tropical convection. Also, it provides the source of predictability in intraseasonal time scale, bridging the predictability gap between weather and seasonal prediction. So this is for those who are not familiar with the MJO. So let me start my real talk. So MJO has been found as a very challenging problem. It is discovered in 1971 by Madden and Julian, but still we don't have any satisfactory theory that everyone agrees. And I'll show you how the conclusion of model intercomparison studies have been in the literatures. So Slingo et al. 1996 compared 16 models. The conclusion was models are poor. Wallis et al. 2003 models are poor. Lin et al. 2006 models are poor. So this is from Lin et al. 2006. They analyzed 14 CMIP3 models. So this is longitude and y-axis MJO variance. So two black lines are from observations, and different colors represent different models, and only 2 models out of 14 captures amplitude of the MJO over global region. But we have CMIP5 models now, right? So maybe we have surprising progress in CMIP5. So this is my analysis on CMIP3 and CMIP5 models. The metric here is the east-west ratio, which is the dominance of eastward propagating waves over its westward propagating counterpart in this band, in this temporal and spatial scale. So in observation, the leftmost for trim data, it's about 3, which means eastward propagating waves has 3 times more variability than westward propagating waves. So in CMIP3 models, I use 19 models. The average of these numbers are 1.79. But in CMIP5 models, I use 29 models, much more models. Average is slightly greater. Also, good news is standard deviation of the number is decreasing, which means we are converging. Let's do some math. So from CMU 3 to CMU 5, we have 0.07 improvement over 6 years, approximately 0.01 per year. And to get observed value 2.97, maybe it takes 100 years. Maybe it's too slow, right? So are we learning anything? Have we learned anything from our studies? Yes, we have. This is the progress I summarized 2 years ago. In the next slide, I will show you revised version of that. I had some revision on this. First thing we have learned is that we know that what component of model configuration is more or less important. For example, in many studies, horizontal resolution has no impact on MJO. Vertical resolution has small impact, not quite big. ARC coupling makes MJO slightly better, but I would say it's minor. The crucial thing we found is convection scheme. When you change convection scheme, you can make MJO in your model better. In that sense, the thing we learned from our previous studies is that we know how to enhance MJO variability in GISS. And the key thing is making the moisture convection coupling tight by changing the convection scheme. I'll talk about this in a minute. And this is the revised version. I found two different models, which were one from GFDL and one from Max Planck Institute, where they increased horizontal resolution, and at the same time, and they coupled atmospheric GISM to oceanic GISM, then they get better MJO. If you just increase horizontal resolution, just couple to ocean GISM, they found no big difference. But when they did both, they get some results that we didn't expect. I'll show you that later too. So let me first talk about how this works. How to make this moisture convection coupling type and how it affects MJO in the model. So this plot is the same plot I showed you to demonstrate how poor MJO in CMU models is. So, and this plot is the similar plot, but I'm using only one model, Seoul National University GCN, and change convection schemes. So the point here is that by changing convection scheme, we can represent the diversity of all different models within one model. This demonstrates, again, convection scheme is crucial for MJO. This is another example. This is results from observation and GISS model. So this is Wavenumber-frequency power spectrum of precipitation symmetric part, and it's divided by its estimated background spectrum. So you can see in this Wavenumber-frequency diagram, MJO feature from observation. And this is the AL4 version of GISS model. No MJO, very weak Kelvin wave. And they did many things in their atmospheric model, and this is AL5 version. You have much better Kelvin wave, but still no MJO. Then I changed the convection scheme. In summary, I increased entrainment rate, but to achieve this change, you have to do some minor things too. Anyway, by changing simply few lines in convection scheme, made this difference. Now we see MJO in this model. So convection scheme is crucial. How it works. Just to remind you that in general circulation models, we represent continuous nature using discrete grid, and the grid has finite size like that. So there should be unresolved part. Typically, the GISS grid size is few hundred kilometers by few hundred kilometers. So clouds are not resolved with that grid. And this is a cartoon about Cumulus parameterization to represent the effect of this unresolved part on resolved circulations. So here I'm picking up mass flux type convection scheme to explain how it works and how the changes in this convection scheme can affect MJO. The reason why I picked up mass flux type convection scheme is like this. So in AMIP experiment in 1996, they have various models, and this is the deep convection scheme they used, and I marked mass flux type convection scheme as red. So, but half of models were using mass flux type convection scheme during that time, but CMU3 models are all using mass flux type convection scheme. And I think it's also true for CMU5 models. So I would say learning about mass flux type convection scheme would be helpful for you. So they first determine cloud base, and they start with some cloud mass, and during their ascent, environmental air are going in, and then the cumulus mass grows, and then when it reaches cloud top, which can be due to buoyancy level where vertical velocity of cumulus, the cloud parcel is 0, they detrains cloud mass. And to compensate this mass flux within cloud, we have compensating subsidence in the environment, and actually this compensating subsidence affects temperature and specific humidity in GISS. So in this framework, the entrainment rate plays a big role, because as I mentioned before, entrainment means how many environmental air is going into the cloud, and the rate of the amount of environmental air going into the cloud would change the property of convection, and it changes circulation, the interaction between cumulus convection and large scale circulation. So one of the ways to enhance MGO variability in GCMs is to make an entrainment rate higher. So if you make entrainment rate higher, then convections are more affected by environmental properties because it entrains more environmental air. So when environment is dry, then your convection will lose their buoyancy quickly, and your convection would be shallower and weaker. But when environment is moist enough, then entraining environmental air to the cloud would not significantly affect buoyancy of cloud parcel, but it increases mass flux of cloud air. And I said the compensating subsidence affects temperature and specific humidity. And if you have greater cloud mass flux, then you should have greater compensating subsidence, and you should have greater convective. That means you have greater convective activity in that grid. So in this plot shows you that the consequence of increasing entrainment rate in GISS model in terms of moisture convection relationship. So basically, this plot is the x-axis is precipitation in log scale. So here's 1 millimeter per day, 10 millimeter per day, and 100 millimeter per day. And y-axis is pressure. And here I averaged relative humidity profile for each precipitation bin. So generally, you have moisture column when you are precipitating more. When you change entrainment rate and make it higher, then you can see that the contrast between the moist regime and dry regime become greater, as you can see in this difference plot between this and this. So difference map is difference the higher entrainment rate version minus control version. So actually the problem is this version of GCM makes heavy precipitation even when the low tropospheric relative humidity is lower than 70%. And by making entrainment rate higher, we somewhat improve that bias. And as I mentioned before, the main point is that in higher entrainment rate version, the contrast between moist and dry region becomes great. In other words, control version of model can make big precipitation regardless of moisture content, but in this version, heavy precipitation only occurs when there's enough moisture. And that aspect affects how the convection in these models are organized in the tropics. So this is somewhat busy and hard to understand at first glance, but I'll try to explain this. So this is Hawke-Miller diagram of equatorial precipitation. Time goes down. This is the high entrainment rate version. I pick up one strong MJO event. So you can see the organized tropical convection propagate eastward like that. And this is the same time, but it doesn't necessarily be similar. But anyway, for demonstration case, I'm showing the same Hawke-Miller plot from control version. The main difference between this Hawke-Miller and that Hawke-Miller is here convection is more organized, but here convection is more scattered, it's everywhere, and no organized feature. And this one, so I pick up this strong MJO event from high entrainment rate version, and using initial conditions from every day, I made 30-day forecast using this model, and was looking at how this organized convection feature changes with time. So this is, so every day I started 30-day forecast, and the second plot is a collection of 10-day forecast. Please let me know if you have any questions. Collection of 10-day forecast. So after 10 days, you lose some organization, and you are starting to have convection like here. You don't have convection, and you started to have convection here. And 20 days after, and now it's more scattered and no organization feature, and it's much similar to that. So this is explained by that. So in high entrainment rate version, you have more contrast between wet and moist region, and the strong convection only occurs over the moist region, but in control version, the strong convection can happen even in dry condition, and it's more scattered, and you lose organization, which is MJO in the tropics. So, okay. Now we can make MJO simulation better by changing convection scheme. Increasing entrainment rate is one way. You can make other changes too. But conclusion is you have to make change that strengthen moisture convection relationship. So then, do we understand the mechanism of the MJO in climate models? I said that we don't have any satisfactory theory for MJO that everyone agrees, but this is model.
Just a quick question here.
Yep.
So I thought this was known for a couple of years already. So why didn't the Simic 5 models actually perform better than Simic 3?
I'll show you later. Yeah. my theory. I'll tell you my theory later. So yeah, God created us. He knows everything about us. We created GISS. Should we know everything about them? So I started this work with Adam Sobel with this philosophy. So this is the physical processes that we think important to MJO dynamics. So MJO has these characteristics. The first thing is cloud radiation interaction. So when there's super cloud cluster and it changed radiative heating profile, and it gives additional heating in the atmosphere, and some theoreticians say it's crucial. And the second is wind-induced surface heat exchange. So when there is convection, when there's MJO-related convection, we observe anomalous westerly over the one-polar region. Because the mean wind is westerly over that region, it enhances wind speed at surface, and it causes anomalous latent heat flux, and it fuels the energy to this convection, and it strengthens MJO, and it destabilizes MJO, and that's the explanation of the MJO in some theories. But not everyone agrees on that. And the third one is the frictional wave cisc mechanism proposed by Bin-Wang. And in that theory, the frictional boundary layer plays crucial role. So when you have convection here, large-scale convection here, you have Kelvin wave response here, which is easterly, and it's just tropically balanced. That easterly, the frictional here is a low, and in this low, in frictional boundary layer, you have meridional convergence below the low tropospheric low, and the frictional moisture convergence over in the boundary layer provides you favorable condition for eastward propagation, and it suppresses the high wave number wave, something like that. So in that theory, the frictional boundary layer is the key process. So using one model, AGCM, with the MJO mechanism denial experiments. So in control model, which we changed entrainment rate and made MJO better. In control simulation, everything is interactive. In no Vichy experiments, simply no W, we prescribe surface evaporation, which is daily climatology, to the model. And in no CRI, no C experiments, in the same manner, we prescribe net radiated heating rate to turn off cloud and radiation injection. And in no frictional wave cisc, no F, we prescribe surface wind stress. Only in this region, because when we prescribe surface wind stress over extra tropics, model blows up because of too strong westerly in the extra tropics. So with so in summary, this is summary table for MJO mechanism experiments, and I said it's single. So in each experiment, we turned off one mechanism. In multiple MJO mechanism denial experiments, we turned off multiple 2 or 3 mechanisms together, then we can see we have more combinations of what has this mechanism and what doesn't have that mechanism. So this is representation of the MJO in a 2D space. I'm not going through the detail about the metrics, but in this 2D space, if you go this way, you have stronger MJO, and if you go this way, it's weaker MJO, and actually this is percentage variance explained by MJO mode. And y-axis is percentage of the variance explained by 30 to 80 day period. So if you go this way, you have low frequency MJO, and if you go this way, you have high frequency MJO. So here you have observation. This is worse MJO version, and this is better MJO version. So we'd like to know what physical process make this difference. So first thing we tried is the frictional wave system mechanism. When we prescribe surface wind stress over the tropics, basically no change in this experiment. And then, so in this diagram, any symbol includes cross means frictional wave system mechanism is turned off in that experiment. Then we see that this. So likewise, any symbol with rectangular means wind in this Vichy mechanism is turned off in that mechanism. So the counterpart of this experiment is this, but the counterpart of cross here, in terms of Vichy, is this. So in this two combination, turning off Vichy made MJO stronger. Is that meaning Vichy mechanism is not important in this GCM? No. Actually, we found Vichy mechanism is important in this GCM. So this is the longitude MJO phase diagram of OLR in contour. This is the purple color means negative OLR. So and time goes up. So you can see eastward propagation of MJO convection in observation. And the shading is evaporation. So red color means positive evaporation. Point is, in observation, evaporation is not in phase with convection, but there's some overlap, some correlation between evaporation and convection. And this is model. The purple contour shows you the kind of eastward propagation, MJO eastward propagation. And in the model, you have more overlap with negative evaporation. So when we prescribe surface evaporation, we don't have any anomaly. The small anomalies here is over land. We didn't prescribe evaporation over land. So in observation, positive evaporation gives energy to the convection, but in the model, surface evaporation subtract energy from the convection. So if we remove this negative feedback from surface evaporation, we get stronger MJO. And this is because the phase relationship between convection and surface wind in model is different from that in observations. So this is similar plot. Contour is OLR gain. Here's MJO convection propagating eastward, and the shading is 1000 hectopascal zonal wind. You have this overlap, and there's no much overlap with easterly, but in the model, you have more overlap with easterly and less overlap with westerly. So in this cartoon, I summarize the relationship between convection and surface wind. Basically, over this one pole region, the mean wind is westerly. And in observation, convection is more in phase with westerly normally. So it enhances surface wind speed below convection, and it makes more evaporation. It fuels energy in convection. But in the model, slightly different. But this slight change makes evaporation weaker and make anomalously negative evaporation below convection, and it subtracts energy from the convection. So the final mechanism we tried is cloud radiation interaction. So in these four symbols we have looked at it before, we turned off cloud radiation interaction. So the counterpart of this one is this one, by adding diamond. So any symbol with diamond means we turned off cloud radiation interaction in that simulation. Is this symbol to that? So here is where cloud radiation interaction is working, and in this cloud radiation interaction is not working. So we found that cloud radiation interaction is crucial in the MJO simulated in this model. Frankly speaking, we don't quite well understand why this is yet, but here's some clue. So this is the Wavenumber-frequency power spectrum I showed you before, and this is the worst MJO experiments where we turned off everything. So we don't have any MJO signal here. And this is the best MJO experiments we had. We turned off Vichy and frictional waves, but cloud radiation interaction is still working. So the difference between these two is that in worst MJO experiments, power has been moved to Kelvin wave part. So it seems that the cloud radiation interaction changes the frequency of the dominating wave, but we are still working on it. So there's some competition between MJO and Kelvin wave, and cloud radiation interaction plays some role in that competition. So let's go back to Professor Chang's question. Here's the paradox in MJO modeling. I told you that we know how to tune the MJO in the model, but I also told you that MJO in models are still poor. So to see whether there's a systematic difference in the other aspect of climate simulation in models, we looked at 10 different AGCM simulations. In this 10 GCM, that includes Marat's superparameterization GCM, also these three pairs, GFDL AM2, Seoul National University GCM, and Eric Maloney's version of CAM3. We changed it, convective parameterization. So one version of this model has relatively weaker MJO, and the other version of this model has relatively stronger MJO for these three models. So let's first look at the eastward propagation of low-level wind. The upper two plots are the lag correlation of U850 from NSEP and ERA entry. And time goes up. So here's 0, and here's minus lag, and this is plus lag. What you can see is you can see some clear eastward propagation. And the base longitude for this lag correlation calculation is over the central Indian Ocean. So from two reanalysis data, you can see eastward propagation. And I grouped 10 models into weak. I think I should show you this first. So this is the intraseasonal variability of precipitation, which is standard deviation of 20 to 100 bandpass filtered precipitation anomaly. And here is observation. And here are models. And I classify 10 models into weak intraseasonal variability model and strong intraseasonal variability model. So for AM2, SNU, CAM3, here is relatively worse MJO, and here is relatively better MJO version.
But the bad MJO versions are closer to the obs.
I'll point that soon.
Okay.
Yeah. And if you look at propagation, as I told you, weak intraseasonal variability model shows westward propagating or standing oscillation, but strong intraseasonal variability model shows some eastward propagation. So overall, this is better than that. So if you make a scatter plot using the two quantities I just showed you, the first one is the intraseasonal variability of the tropics, and the second one is the eastward propagation. Then you have observation here, and the weak intraseasonal variability model, relatively weaker intraseasonal variability model, I marked with open circle, have lower east-west ratio. To achieve this observed east-west ratio, we have to increase intraseasonal variability too much, like here. So in this strong intraseasonal variability model, east-west ratio is similar overall on average, but your variability is excessive. And this plot is same one. Now I have gray circles that I showed just in the previous slide, and the red circles are GFDL high resolution AGCM. It follows a similar line, but when they couple this GCM with ocean GCM, they go this way. So that's why I revised my summary of recent progress on MJ modeling. So when you increase horizontal resolution and then you couple to ocean GCM, you can achieve variability and propagation together. Let's go back to the issue about the paradox in MJ modeling. This is June, July, August mean precipitation. The order of model is same. This is observation, and this is weak intraseasonal variability model and strong intraseasonal variability model. Clearly, you can see that these models are over-simulating, making excessive rainfall over the one pool. I don't have plot here, but if you look at winter, you have too much precipitation over the SPCG region. So the Northwestern Pacific during boreal winter and SPCG during boreal winter, they are the warmest ocean in the world during that season. So my simple interpretation is like this. So in the tropics, you have warm region and you have cold region. The height of arrow represents the strength of convection, and the circulation between warm and cold part proportion to the gradient of convective stream heating. And this is in case of less sensitive to moisture convection. And if your sensitivity to convection become bigger, then you would have bigger contrast between warm and cold, and your circulation become too strong. I should say that without negative feedback from surface. The model I showed you is all AGCM, so they don't have negative feedback from surface when they have high, strong precipitation. Okay, can I take 5 more minutes? Yeah, maybe it's too late. So this is my personal view on the MGO problem. I would say MGO problem is cumulus parameterization problem, and cumulus parameterization problem is understanding how cumulus convection interacts with environments. There are 2 approaches for this problem. The first one is remove this problem. We can resolve cumulus convection. The global cloud recharging model, global larger dissimulation is slowly becoming practical, but I would say my goal is not to beautifully simulate MJO, but to understand the interaction between cumulus convection and its environment. The second one is challenge the problem toward a perfect cumulus parameterization. Maybe it's impossible. But if we achieve that, and we are making small achievement toward this goal, at least someone on the earth understand it. So I would also say that I want to also say that we need smart people to solve this problem, like you, Steven. Let me show you first the example of the problem in cumulus convection. This plot shows you the joint relationship between precipitable water and precipitation in log scale in the tropics, in the one-pole region. This is from the SSMI, TMI precipitable water and GPCP precipitation. This relationship. And this is the strong MGO version of GISS GCM. And weak version of GISS GCM is similar. The point is that when your column is moist enough, like here, 55 or 60, you still have some days where you have very weak precipitation. But in the model, you don't have such days. If your column is moist enough, you always have heavy precipitation. I think it's big. So my thought on this is, in observation, cumulus convection is not deterministic. It has some stochastic components. So with same temperature and moisture profile, sometimes it gives more precipitation and sometimes it gives less precipitation, and it is not well represented in current convection schemes. So to better understand, to learn something about this behavior of cumulus convection in the tropics, I went to Maldives last year to attend a field campaign, Dynamics of the MJO, and I was working with radar people for 3 weeks there, and since then I'm analyzing radar data. So in the next 2 slides, I'll be showing you the one results from my analysis on this issue. So using radar data, I tested. So first, I should say that there is one physically based stochastic parameterization for deep convection developed by Plant and Craig. And I'm not going to go through this formulation, but the point is that the convective mass flux has some probability in their formulation. And to construct this formulation, they assumed something about cumulus convection in nature, and one of them is that this one, cloud number distribution is governed by a Poisson distribution. So if the mean number of cumulus cloud is large n, they assume that the probability of cloud number small n follows Poisson distribution. And using the ground radar data, I could classify the reflectivity blobs into convective and stratiform, and I was looking at the convective entity in the ground radar data, and this is the result. So each plot shows you that the collection of different snapshots. So the first plot, I collected the radar reflectivity snapshots where the convective elements, the fraction of convective elements is between 1 and 2%, and 2 and 3%, 4 and 5%. And here the mean number of convective element is 5. And in this plot, the dashed line is Poisson distribution predicted by the planting theory, and the bar is the data from data. So you can see that the assumption in the existing stochastic convection scheme works very well, at least until this total fraction of convective entity is below 5%. After this, after 6, 7, 8, 9, 10%, still works reasonably, but we observe some deviations from that. So this is my short version of how we should tackle MJO problem and cumulus convection problem. Actually, next slide is summary. But maybe I'm not going to read this, but we'll take questions. Thank you.
Questions? Yes, Mara.
One of the reasons why so many models don't have good MGO, because many of them know this is like, since the Kyoka kind of introduction of the parameter that you make this modification and you kind of get MGO.
Mm-hmm.
But as a price for that, you basically destroy the new climate. Like this has been known. So that's why most models kind of choose to have good climate rather than good MGO.
Right.
Can you comment on that? Why we cannot get one or the other? When you get your modifications, do you destroy your climate too?
Yes. Yes. I think this is one reason. I mean, first of all, this one.
Yeah.
Over. So here's the warmest ocean over in the world during this season. So if you strengthen moisture convection relationship, then if you don't have negative feedback from surface, then it's hard to break down this positive feedback between heating and moisture conversions between warm and cold ocean. So the first thing is the coupling, but we know that in couple models we don't have good MGO also, and in my personal experience, if you change entrainment rate in couple model, your radiation balance becomes weird. So you have to tune the other parameters, and it seems that it's hard to come up with some parameter combination that gives you better MGO and better mean state. So I was thinking maybe we have structural problem in convection scheme. One is this stochastic nature of cumulus convection. The other is, I'm not working on that, but many people like Brian Mabs, Sung-Soo Park, and French people are working on the organization parameterization or cold pull parameterization. So you have some memory of cumulus convection from this time step to the next time step. Yeah.
Yes, Mingguan.
Yes, so you described some denial experiments, and therefore the radiation and the wish are important.
Yep.
Then earlier you talked about the entrainment rate. How do you connect these two? Say you can still have wish and radiative, say, interaction, but if you change in the entrainment and the entrainment rate, the MJO could decline.
Yes.
So how can we explain the mechanism using these two separate things?
Yeah. So cloud radiation interaction and the Vichy, they are processes Okay, one way to explain that is entrainment rate is also one of the processes for better MGO. So you need, in my talk I said cloud radiation and wish is important, but maybe I should say cloud radiation and wish and higher entrainment. Three of them are important. Yeah. And the entrainment rate is crucial. So without entrainment rate, higher entrainment rate, you don't have good MJO even you have cloud radiation and
That's right.
yeah.
So the conventional way, or say the way people have been thinking about the mechanism, either wave or radiation interaction or frictional
Yes.
wave system. It seems like these mechanisms alone are not sufficient to get to the MJO.
Yeah. There's another school of
Other things
Yeah.
like the entrainment.
yeah. The another school of theories, the moisture mode theories. So they are more interested in the gross moist stability and less interested in the static stability of the atmosphere. So in that perspective, in that theory, the moisture sensitivity of convection is crucial. So I would say entrainment, you can translate entrainment rate as the proper moisture sensitivity of convection to environmental moisture. So proper moisture sensitivity, proper convective radiation interaction, and proper Vichy, they seem important for a good MJO in model. But actually the suggestion in our paper was to do these kind of MJO mechanisms denial experiments using many models. Then we may have some consensus about okay in current state of the art GISMs, the main mechanism is, for example, cloud radiation injection, or it's all different one. So that may give us some insights about any mechanism of MJO in models.
I actually have two questions related to both the questions that were already asked. One is that you showed that obviously the MJO was really sensitive to the convective parameterization.
Yep.
I guess I was just wondering about how well these models represent this dynamically, because if they're failing dynamically, if we can get that better, would that sort of mute the impact of changing convective parameterization? So maybe it wouldn't be quite so sensitive. So if we got the actual dynamical processes correct, like circulations and things like that, more accurate, then maybe it wouldn't be quite so sensitive to parameterization. Is that possible?
Could you be more specific about the dynamics?
I mean, obviously it's a complicated system, so anything, just improve it. I'm not really sure how you would go about improving it, but say if we captured, the circulations associated with the MJO, the dynamical circulations associated with maybe potentially, they would be able to override any issues that the convection parameterizations are going to have, because obviously they're going to be prescribed, flags. Okay, we're going to go off now because X, Y, and Z doesn't matter. So would that be a way to go rather than?
But aren't those dynamics controlled by the parameterization? Like the wind circulation, isn't the parameterization designed to figure out how the effect of convection on the surrounding wind field?
That's right. So I would say convection and dynamics, let me say circulation, they are tightly coupled.
Right.
Yeah. So I think it's hard to separate, hard to looking at dynamic circulation separately without thinking convective parameterization.
Or
Because
explicit modeling, as you said before.
what's that?
You could explicitly model it if you had a high enough circulation resolution.
Yeah. Yeah.
So what's the answer
Uh-huh.
at this question? So I think what you are saying is that if convection was properly modeled, then you don't have to make these adjustments.
Right, yeah.
So, but that is really the big question. Right? There are all these parameters in models are highly parameterized, and when you change one parameter, other processes are affected. So.
Right. I guess that kind of relates to the second question that I had, that that you performed all these sensitivity experiments after you performed the modification of the entrainment rate. Did you try them before the entrainment rate?
Yeah, we tried.
Did you see the
Same tendency, yes. Same tendency. But in the first version we had that plot, but it was too complicated. I mean, too many dots and symbols, so we just threw out the weaker MGO. So when you turn up Vichy in weaker MGO version, you get stronger MGO also.
Yes, Malcolm.
I'm an oceanographer, okay, so why is there no MGO of the Atlantic Ocean? Is it the distribution of land, or is it the oceanography? What's different between the Pacific?
I think it's SST.
It's too cold over there.
Too cold?
Relatively colder than Indian Ocean and Western Pacific. I think that's the main reason.
So that gives you less convection?
Yeah, so upscale organizers.
Likewise, we don't have MGO convection over Eastern Pacific
Yeah.
because it's colder than western part.
Yeah, but due to very strong linear bands, for example, MGO propagates from the east to
Farther.
Pacific. So it tells me that actually sea surface temperatures are very important.
Okay, so let us thank Dr. Kim for presenting.